we now finally want to test our CNN and also want to create an actual CNN and run it. So we have quite a few functions in our network now. And what we should do in the first place is to run the forward part, including the convolution layer, the ReLU layer, max pool, and just run this like with 3 different layers so that we see how the information is passed on from one layer to the next layer. So when we have a forward pass, it creates an output that fits to the next forward pass of the next layer and so on. And also please try to use different numbers of filters, different padding, different step size, different kernel size. The idea behind that is that we want to make sure that the matrices are handed over in the correct way so that the shapes always work. And we also want to take a look at the resulting data. So for example, the images, and see whether they make sense in principle, so that it produces something that we can expect and that makes sense. So for example, when I just use the first convolution layer, I feed in an image and I pass it on, then it should look like this, for example. And of course, we should not get an error message. And giving on the padding and the stride and the filter size, we also know how large the output image should be. So we can do the math and also check that. And of course, we did this already while we were building the convolution layer and the ReLU layer. But now the point is, of course, that we see how the images are handed over from one layer to the next layer. So we want to also check the ReLU, the max pool, for example, and then we want to feed into the next convolution layer and so on. And you see when we add padding, for example, we should have an edge at the image. And you also see how the network kind of digests those images. And at the end, that you just have like image with lots of pixel, and you feed it into the dense layer. So something like that. So therefore, let's test this. So I want to go back to our script where we test everything. And also here, I set up a new folder, which is called testing. Okay, so we load our ANN. Then, of course, we want to load a few images, let's say 5. And maybe just don't take the scaling too small because we want to pass it through a number of different layers. And usually it's getting smaller and smaller, each layer, so that we eventually still see something so that we have an image of a considerable size. And then we also want to plot that. So we want to take a look at the convolution output, the max pool output, and many other things. So we just, first of all, import the network and the images, of course. Then we import all those layers. And we import and we then run the convolution and the max pool. And of course, we want to create a plot. And then we want to take a look at those images. So I checked a few images and you should do the same. So first of all, it should run without any error message. Then if you look at the images, that's the output of the first convolution layer. Then we have the output of the first max pool, then convolution again, second max pool. Then we also added padding and so on. So in principle, you should see a pattern like this. And of course, we also want to test the backpropagation part. So let's also see what we expect to see then. So I want to return to the slides. So what we will do now is that we just take the output and put it into the backward method of the last max pool layer, and then we pass it on to the backward method and the ReLU layer and convolution layer and so on. So we do the same thing, but just backwards, because we also want to check how or whether the sizes and shapes of the matrices make sense and that I don't create an error message. So we would then start with an image that just looks like this. So that was our last output image, which doesn't seem to have any significant structure. But then we just put it back into the max pool. Then remember the max pool. Then in the backward method, we just get only those pixel values highlighted, which have been a max. Then we put this in the reload, which doesn't change anything. It's just a reload. Then the backward method of the convolution layer, and then we just continue with that. And again, you have to reload, make sure that you really see it's only because it's only passes the positive values, but doesn't change them. You should have the same kind of image. And then from the convolution part, you should also get, if you go backwards, images which are larger, have more pixel. And then you can again see how the network kind of digests the images. And of course, when it's learning, it does something else because these would be the inputs. That would be the feedback at the end from the loss function, which we don't have here. But in principle, then it all seems to work, which is of course not a guarantee. But at least if you don't get an error message and if you see plots that look like this, then it's almost pretty certain that the code works. So I also want to do this here again. So we can just run the backward part and also just plot those images and see what we get. And let's take a look at the plots. So and here we have the images from starting from the lower layers going to the upper layer, and then you see those structures I have showed you earlier. Again here, of course, the color scaling can be a bit different, depends really on the pixel value, but you should definitely see those structures that I also see here in the plot. And that's also a good sign that your backpropagation methods also work. So of course, that is still not a proof. So now we have to, now we want to build an actual convolution neural network. And we have all the ingredients now. So we have the so we have the convolution layer, of course. Let me just go back to the code so that we take a look at the code. So let me just delete this here. So we have all the convolution layer, of course. So we have the different pooling methods. We have the different activation functions and everything. So we have all the ingredients. And again, so we have talked about the average pool layer and how to implement it, including backpropagation. Sorry, not the average, the max pool layer. And I added the average pool layer and also the min pool layer. So so that we have all these different pooling layers. And please feel free to download it from my GitHub repository so that you have the ANN with all the different layers. Because as I said, we have only discussed the max pool layer because it's the most difficult, I would say, concerning the backpropagation. So point is we have all these different functions and ingredients now. And now we should be able to create our convolution neural network. You have probably noticed already that when you run a few layers or so on your computer at home, for example, you have just a laptop, it takes a considerable amount of time. So the thing is, if you want to really build a large network that is really able to distinguish between cats and dogs, for example, we again could do that. We have the ingredients, but they are rather complicated. So I just want to show you an example, what it looks like. So they have many different layers, let's say 100 layer, 50 layer. That's actually not very rare. So those networks have really many layers. And of course, our network is not optimized concerning runtime and speed. So it will take relatively long. So we can't really build one of those. I mean, we can do that. As I said, we have all the ingredients. So we can build such a network, but running and testing it properly as a first step would be too long. But just that you get an idea about those networks. But we can still actually build one, which we can test in an acceptable amount of time. And it's one of those first convolution networks, and it's called LeNet from Jan-Lee Kun and co-authors. And it was one of those first networks which were really able to categorize between different images. And in this case, it was handwritten digits, just numbers. Let's, for example, you have a zip code on a letter and you want to automate the process in sorting them. So you take an image and then you categorize those numbers, and then you know, okay, that's this particular number, that's this particular zip code. And since it was one of those first CNNs that were able to do that, and the task is relatively simple, so just looking at those numbers and categorizing those numbers, which is a lot easier than, for example, distinguishing cats from dogs. It doesn't require a very sophisticated and complicated network. So then the LeNet is the network we can actually build now and really test. So and that's what we're going to do now. So it has only 7 layers, and I just want to show you the structure of the LeNet first. And again, I like to mention that modern CNNs like ResNet or so, which is a particular architecture of a CNN, GoogleNet or so, they have 100 or more layers. And again, we could build that. So we have all the things that we need. Okay, so, but you probably do this on your computer at home. You don't have servers. And it's, again, not optimized for speed. So we want to stick to the LeNet architecture and want to rebuild LeNet. And let's see whether it works. So first of all, what is the idea? So we have those numbers, and they're black and white images. And we feed them into our first convolution layer, which contains 6 filters and has a size of 5 times 5. So every filter and no padding in stride 1. So if you look at the paper, that's pretty much the structure of the first convolution layer. Then we pass the information to an tangents hyperbolicus that we already have, then an average pool that we, as I said, that I included in our network, and you can download it if you like from the GitHub repository, or you can just rebuild it based on the max pool layer. Then we pass this on to the next layer, which the next convolution layer, which has 16 filters, and so on. So then there's next convolution filter, and then there's our flattening part, and then there's our dense layer. And the dense layer has 85 neurons. There's not the version of the LeNet. There are different subversions, but that's the basic architecture. And you see it's a relatively small network, has only those 7 steps or so. And the difference now is that we have in tangents hyperbolicus as an activation function we implemented already. So we have only 3 different convolution filter. There's actually also one thing I want to show you then in a few seconds, that from convolution layer 1 to 2, not all the channels are combined. Remember when we performed the convolution, we did this for all filter and all color channels. And then if we have one filter for the different color channels, we just sum it up. And then we pass it on to the next layer. And we did this with all channels and all convolution filters. But now there is a filter in between, which does not allow to do this for all combinations. So some color channels are not convolved with some of the convolution filters. And then we have this average pool, which is also a difference, which in this case makes more sense because we just have black and white images. So we don't have a background or foreground that has to be recognized. So max pool and min pool doesn't really make sense. So how does it now work with the, so first of all, that's our structure, but how does it work actually with the, that not all channels are combined? Well, it's pretty easy. So if you look it up in the paper, then you see when you go from convolution 1 to 2, so you will have, so let's go back to the overall structure. So you have 6 filter, and then you have 16 filter. And the enumeration is already in Python style, so they start with 0, so they have all the 6 filter, which is then the number of channels if you feed it into the convolution, second convolution layer, and then you have 16 convolution filters or convolution kernel. And 0 and 0 will be combined, 1 and 0 and so on, but for example, not 0 and 2. So the easiest way how to do that is just to build such a matrix. And then put it into an if condition. So first of all, we can say, okay, if we have 6 input channels and 16 output channels, then we are in the case when we have the information going from convolution layer 1 to 2, and then we just apply this array. And then somewhere in our nested loops, we just say, okay, if this filter value is 1, then we just perform our calculation. And let me just show this quickly before we continue. So I want to show this. I implemented all this already, so I don't want to really show you explicitly how that works because it's pretty simple. So I put the reference in the code of the paper where they discuss it. So here is the filter, and if the number of channels has a particular value, then we build this filter, and then we perform our operation only if the combination of C and K equals 1. How they actually came up with the idea that some combinations should be done and some not is not really well explained in the paper, I have to say. At least I couldn't really see that, or at least to my knowledge, that's not really a straightforward mathematical derivation why it is exactly this pattern. You can kind of see that it's kind of repetitive. So there's some symmetry behind that. That probably makes sense. I just guess now, it's just guessing, that it was just kind of trial and error, and just turns out that when not all combinations are performed, the performance of the network is a lot better. Then we have another thing that we add. So that's the instead of the max pool, we have an average pool, and that's also not so difficult to implement. So then we have just current slice mean, and then we have the mean, and also in the back propagation, we have to take this into account. However, if you calculate the average, what do you actually do? You add up those values and divide by the number of values, which will be left as a derivative. So you have to multiply the inputs, the d-values, in order to get the inputs. You have to multiply the d-values with 1 over the number of pixel you have calculated the average from. Because again, how does the average work? You sum up the values and divide by the number of values, which is the size of the filter, so xk times yk. And then if you calculate the derivative of that, then you have this as a prefactor. So you multiply 1 over that with the d-values to get the d-inputs. And then we need a data set. And this is the so-called MNIST data set, which contains all those numbers. So again, let me just go back to our script. So I want to show you the average pool once more. So you have just the average pool here. And the only difference in a sense is just this, but it has still the same structure. All right. So then we load the corresponding data sets. So let me just remove that here. So the data set is in Keras/TensorFlow, so we just install the dataset and then we just import a dataset. And I want to show you how to call the dataset. So the dataset, so I prepared this here already. So it has just the command load data, and then it generates a tuple as an output. So the training data, X, these are just the images, and Y, these are the categories. And then you have the same structure, but for testing. Because what we want to do now is we want to train our network and then want to test it with data we haven't used for the training. Because otherwise it doesn't make sense. So let's load the data. Let's take a look at the shape of those matrices. So first of all, let's take a look at train X. So what is it? It has the shape 60,000 times 2828. So that looks pretty much like 60,000 images. They all have the size 28 times 28. So let's plot this. Let's, for example, plot just train X, and then we have just one image, all rows, all columns, and just take a look at the first one. I guess it's a 5. Then we have another one that's a 2, and so on. So, and those images, we can also take a look at those images. So I equals this, and then we see that it is just black and white. So first of all, we see that because we have only one color channel. And then we have just the different values for gray. So we have 0, of course, and up to 255. So it's an 8-bit image, which is good because that's what we are kind of used to. And then we have the different scales and grays. So we can also just say we use another color map and then just say C map equals gray. And then we have the images with a different grayscale. So we have our images and the test data set. When we want to test and evaluate our network, has the same structure. It's exactly the same thing. Of course, we have fewer images than we have the training, but it requires 6,000 images, so it's quite a lot. They're relatively small, 28 times 28. Remember, our scale was like 125 to 250. When we just tested our network, we had way more pixel. We can't use our read and scale now, but we can rewrite it if you like. But there are a few more things we actually have to do in order to feed it into our network. So first of all, our network expects the following structure. So if we, for example, go back to our convolution layer, then it expects the structure. So if we just scroll down, so we have the coordinates X and Y, then the number of channels, then the number of kernels, and the number of images. And depending on the image, so it's always the coordinates in the image, then we have either the number of channels or the number of kernels, and then the number of images. However, if we just look at our data set, it's the other way around. So what we do now is before we build the LeNet, and I want to show you that, so we can build the class myLeNet, and in the init, we can first of all call the data set, and then we transpose the data set and rearrange it so that it has the shape that we want. So also here, I prepared it already, and it's in the GitHub repository. So when we just run this here, and then we just want to check whether we have the same shape that we need. So if we just say train underscore X, and then take a look at the shape then you see it has the correct shape now. But still wouldn't work because our ANN expects to have a 3D image. So we now turn it into a 3D image. And that's what we do here. So again, it's the code is available online, so you don't need to do that. But of course, I show it here, and we can run this code, of course. So then we just, first of all, rearrange it, and we call it test x3D. And then we have the image arranged, or the images arranged in the order we needed it. And we also have 3 color channels, but it's always the same information, so it's not cheating. So remember, we implemented something like that already in our read images class. So these are the images, but what are the classes? And that's what we have here in train Y. And remember, the shape had to be the length times nothing in order to be understandable for our optimizer. And that's what we have here already. So it is apparently a sparse vector. So we can just print the first entries, let's say from 0 to 10. And then we see the first entries, and that's the, so these are the different classes. And of course, the number of classes is 10. So let's also check this. So let's, for example, use unique and then use it for train, apply it to train Y. And you see we have 10 different classes, which of course corresponds to those numbers. So, and that's all those lines I just put into, so I created a module, I called it class my LeNet, where we first of all have an init. And in this init, we call the dataset. Then we rearrange the dataset and we save it. And we also do a few things like, for example, determine the number of images. So I want to expand this a bit further, that you see all the code. So we in this part we just load the data set. Now we want to run the training, and we want to run the training with the LeNet. So we have to build our LeNet. So we have to determine the mini batch size, the number of iterations we want to have per mini batch, and the number of epochs. So how often we want to call the mini batches and iterate them 10 times. So you saw already we have 60,000 images. So actually this number should be a lot larger, but fortunately that's not really required to get an acceptable accuracy. Then we have the learning rate, the decay, a momentum, maybe 0.5 makes more sense in this case. And of course, and there's something else I want to show you later. So, but first of all, we set up the particular LeNet. So according to the paper, we have 84 neurons in the dense layer. We need 3 convolution layers. Of course, we need to know how many classes we have because that's the number of output neurons. Then we need the average pool 2 times. We need the tangents hyperbolicus 4 times. I call these instances here in a comprehension loop and save them in a list just for convenience and because it's all the same. And we need a flat layer. And then we need the 2 dense layer. So we know, of course, how many neurons we need because that's what you can read in the paper. We also know how many classes we have. That's what we have in the data. How do we know how many features we have once we pass the information from the flattening layer to the first dense layer? Well, actually, we don't know but we can do the math if we know what the convolution filters are, how large they are, and what the padding will be. So you have to know this number. An easy trick is, of course, to add a function that always does the math for you and then feeds in the inputs here. So that's actually how you really do that. But I don't want to make it more complicated. So in our case, we can do the math and see that at the end, when we has the flattening layer, one image has 480 features, and that's the n inputs. And then, of course, we need the calculation for the loss, and we need the optimizer. So let's skip this part here, and I will explain this in a few seconds. And now let's actually start with the LeNet. So let me first of all start with the inner part. So we call the convolution layers the activation functions and the pooling layer according to the paper in the LeNet. And then we have the entire forward part. And after the forward part, we calculate, of course, the predictions and the loss. So that's what we do here. And then we also can calculate the accuracy. And of course, we just do the whole thing just backward. So that's really something you really can do now with your network. So we just go backwards. Then remember, we have to pre-update our parameters. And then we also have to update the weights and the biases in the convolution layer and the dense layer, and then we have to post update the parameters. Remember, that was for the decay of the learning rate, so to calculate how many iterations we have, and for the learning rate decay. So we can run our optimizer that we used already for the dense layers on the convolution layer. Why? Because we wrote it this way. So if we just go to our optimizer, if we just scroll down to our optimizer, it was looking for the attributes, weights, and biases. So even if it has momentum, it would add those momentums with weights and biases. And it also always looks like D weights, D biases, and so on. And we wrote our convolution layer. So if we scroll up now and look at the convolution layer, so we wrote our convolution layer in the same structure so that we call the biases, and the values in those filters, the kernel values, we also called weights. And of course, these are the learnables that have to be adjusted. So they are called weights, d-weights, biases, and d-biases. So this is why we can use our optimizer now. Also here, ignore this for a moment. I will show you later what it means. So the point is so we just set up our network, the forward part and the backward part, and then we can apply the optimizer just as it is, as we have used it for the other layers in the earlier lectures. And then, of course, we want to monitor, as usual, the accuracy, the learning rate, and the loss. And we also want to create nice plots. So this is what we do with a number of iterations, like 10 for one particular mini batch. And of course, I do this like 10 times, and then I have to load another mini batch. And that's what we do here, outside of the loop. So we know the total number of images, and then we randomly sample it, as we did before already, when we called our images with cats and dogs, that we have our mini batch size and randomly select images without repetition, and of course the corresponding classes. And then we run this with the number of epochs. And of course the optimizer then changes the weights and the biases accordingly, and we want to save those weights. And just in case we have to interrupt our code, and want to restart it. But we don't want to start from zero again. So we really want to start from the weights that we had already. We can save it. Then, of course, we can call those weights. And that's what I added here. So I have this option that we want to add these weights. So if you just put anything else than no, then it will just start with those weights. And no is the default setting, so that you know how that works. So we can really, so if you just look at this, so this is just really our network that we have created. And we just create our Lee network, the forward part and the backward part. And everything else is similar to what we had in the first lecture when we created our neural network without the convolution part. And I would recommend really to try this from scratch. So try to do it yourself. And of course, if it doesn't work, don't worry, the code is available online. So let's take a look now at the result. So we just import data. We did the training. So we have a training data set and a test data set. And the vector y with the classes is already a sparse vector. And then we have those images here. And we have to rearrange those images. So, and then you can actually play with the LeNet and see how it digests those informations from the different images, from the different numbers. And that's what it really does. And then it feeds it into the into our dense layer. And now we do the backpropagation. All right. So then as I said, I prepared this function already, or this module I called myLeNet, and it runs the LeNet from our ANN based on the MNIST data set. So you just call it LeNet, then say .run training, and then we can run it. So let me just show this. All right, so let me just first of all call the myLeNet. So we have our LeNet here. So myLeNet. We don't need any input for the init, so let's call it my LeNet equals my LeNet. Then we initialize it, so it loads the data set, and then we run our training. So we just say run my LeNet, and then we just say run training. And let us just run it for a mini batch size, which is relatively small, so that we can actually really see the progress. So let's say mini batch size equals, I don't know, like 5 or something. And then we run it. And in my case, of course, the computer now is a bit slower because I'm recording the lecture. I have several number of, I have different monitors and so on. So you can see that it learns. So even though we have a very small mini batch size, 5, which is really not a perfect number, but you see the loss goes down and the accuracy fluctuates a bit. That has to do with the small mini batch size. So a larger mini batch size would make more sense. Now it started a new mini batch, and then of course the accuracy goes down and the loss goes up. But in principle it works, so it learns. So let me just interrupt that. And mini batch size, which kind of makes sense, is I would say more than 100, because then you have each class in average 10 times. Let's say 124. It's a nice 128. It's a nice number. So let's see what we get. And that of course takes a bit longer. So I want to show you already the result. So if you do that, so I go back to the PowerPoint. So if you run this, let's say with a learning rate, it starts at 0.1, a certain momentum and a decay, then you see that the accuracy goes already up after, I don't know, like a dozen, 2000 of the epochs. So especially after 100 epochs, you should really see a progress that you have an accuracy above 75%. So what happens is that you load a mini batch and it's optimizing everything for the mini batch. And then you done with the mini batch and add a new one. And of course, it's a new data set. So the accuracy goes down and it goes up again and it goes down and up again. So that's actually not a ideal learning curve. So that actually does not really look nice. And when you're not lucky, then it even drops dramatically. So the problem is every time it loads a new mini batch, it drops and then doesn't really see or show a nice learning curve. So it kind of gets stuck. And the problem is why. So if you really run it as it is. And when you do this and take a look at the weights, right? Remember we saved the weights. Then you will find out that it's also almost certain that it happens in your case if you just run it as it is. Then the weights will have large values. So it tries to optimize it by having large values. And that's a very typical problem. And of course, we don't want to have that because that's pretty clear that somehow it got stuck. And apparently, if you look at the learning curve, the accuracy, the loss, how it changes, the training process is not optimal. So we somehow have to penalize large weights. So we have to tell the network having large weights is not a good thing. And you can do this with so-called L1 and L2 regularization. And that's what you saw in the code and I want to explain it now. So we want to penalize large weights. So how do we do that? So if we just go back to our gradient descent with our momentum, for example, remember mu was the momentum. And then we can add a linear or quadratic term there. And just remember, it's the gradient. So we are having the change with respect to something. So that's the first derivative already. So if we, for example, add the L2, that means we have our parameter raw, and we multiply this with a value L2. That's a new hyperparameter. And the idea is that this hyperparameter is still relatively small, but if our parameter is large, so of course the gradient can be 0, but it might be that our parameter is large, like the weights are large. And if you multiply this with a value, which is small, but the product still is not 0, then you shift the gradient away to this particular point if the weight is large. However, if the gradient is 0, and if the weight is relatively small, then the entire expression here is 0 as well. So the algorithm would stop. So that's how it works, right? If you have a large value for your weights and you multiply this with your L2, it will prevent the overall equation from being close to 0, even though the gradient is 0. So it will go away from that. And that's something we can implement easily. So there are, again, different ways how to do that. But the easiest way is to go into the init. And for example, in our case, we can hard code it. You can also put it as a parameter in the init when you initialize your class, that you have this as an input parameter. I again wanted to keep it simple. So I just set a particular value, 0.01, and then we want to save this, and I also want to show you how to apply this. So I just go back to our code, and you see it's already running. Again, in my case, it will take a lot longer than it will take in your case because my computer is recording, and there are more than one monitors on the computer. So, but let's take a look at the ANN. So we can also close this here. So first of all, let's go to the init. And that's where I added the L2. So this is just another value. And again, if you like, you can put this as an input parameter. And then if you change those learnables according to the derivatives, you add this product. Because if the biases and the weights, if they are large, this will be also large. Therefore, the biases will be large and the gradient will not, the overall sum will not be zero, even though the gradient itself is zero. So if you go back to the optimizer and take a look at the optimizer and take a look at this equation at the end, then this value will be a bit larger. So that will take this into account. And if you just do that, so if I go back to the PowerPoint, so if you implement this, and run it again, it will look better, but still not perfect. You see now that again, it fluctuates, but it's not like before that it really goes up and down, up and down. Still, it has some glitches, but maybe you also notice it goes up a bit faster, but it still has these glitches. And that's now also one thing we just can take a look at. And that's the, and you can solve this problem with the mini batch size. So what happens? So if the mini batch size is too small, then it optimizes for a very specific subset of the data. So for example, of the mini batch size, let's say it's 5, and you even don't have all the classes. And let's say you have lots of numbers that like 0 and 6 and 8, which all have these curves, then the convolution filter get only sensitive for that. Whereas if you have numbers like 7 and 1, where you have straight lines, would trigger completely different convolution filter weights. So therefore, if you have a small mini batch size with too many iterations, it gets stuck in a local minimum for the very specific mini batch. And that's, of course, something we don't want to have. So we want to avoid that. How do we do that? Ideally, we don't need to have a mini batch size. We just run the entire data once, but that's impossible because it's too much data. So therefore, we still want to have a large mini batch size. So what my computer conveniently can do without getting frozen is like 512. So that's the largest value in my case. And then do not run too many iterations over one mini batch, because then you still have the same problem. Even though it's large, it will find a solution for our mini batch. But then if you load the next batch, then the accuracy will go down and the loss will go up. So we'll still swing up and down a bit. So do not run with too many iterations. So in my case, I figured out like with 10 iterations, that works perfectly. And then the learning curve looks like this. You still have these fluctuations, of course, every time you load a new mini batch, but that's completely normal. And again, so the rule of thumb is mini batch size as large as possible, not too many iterations, because otherwise you can get stuck in a local minimum. So the mini batch size has to be large. So, and then we run our neural network, and then we can also evaluate this. So let us take a look at the network. So it's still running in parallel. So I'm recording here. And you can see that the values are improving. But of course, they're not perfect yet. So it's been only the 4th iteration. but you can see that the accuracy is already relatively large compared to the mini batch size. So we have 10 different classes. So 10% accuracy is just by chance, and this is significantly larger already. Still, the loss, of course, is still very high. We have 10 classes. Remember, the loss is calculated via the cross entropy, and if it's completely, so if it doesn't, so if you want to see whether it's still random or the network is guessing in the correct way and it's not completely random, you can easily calculate this because we have the entropy, which has the ln. Then we have 10 classes and we sum up over 1/10th. So it is just ln 10, which is roughly 2.3. So if your loss is below 2.3 and significantly below 2.3, so there's always a numerical inaccuracy. But if it's like 2.1, then you can actually tell your network's on the right way. It is beyond just guessing. It is kind of assigning these classes not only randomly anymore. So there is some weight in having correct assignment, especially if you have a large mini batch size, because then it's pretty unlikely that it's completely random. So you see that so it's improving. I want to stop this process here now. And we can also, of course, call the old weights that I had earlier. So just say save weights, yes. And then you will see it actually makes a larger jump. In the meantime, let's go back to the PowerPoint again. And what I also added is a class that's called evaluate my LeNet. And after you're done with the training, so after it really, let's say it really looks like that, and you can see it's after 50 epochs, 10 iterations, then you definitely have an accuracy of like 95%. Then you can evaluate LeNet, and you can do this with the class evaluate my LeNet, and then you can compare the predicted to the actual. So let me just show this again. So I added a class, so it does still the math here. So, and I added a class. So after run training, there's a class that's called evaluate my LeNet, and it just picks n images randomly and runs it through the forward part again with those weights which have been saved after the training. Here's the forward part. Then, of course, it calculates the probabilities from the softmax, and then it compares the predicted class to the true class, which we, of course, have from the class vector. And it creates a nice plot, and it also shows you the predicted class and the probabilities as an output. So, and then you can compare those numbers. So I did it after 500 iterations times epoch, which had an accuracy like 85%. So for example, 1 and 3 was a misidentification, and you can look at the probabilities if you like. Then you have 4 and 5. So 4 was pretty likely, 9 was also relatively likely. And if you look at the image, you could actually guess a bit. So that looks close to 9, it could be a 9. So you still have some misidentifications, but you also, of course, should have most of the time the correct identification. And what you see here is the histogram of the probabilities, and that reflects the knowledge of the dataset. Remember when I said in the first lecture that entropy has nothing to do with order or disorder. Entropy has to do with the amount of information we know from the system. And you can actually see that here. So if we really know it is an 8, then we have 100% here. So the probability is 1 and 0 for all the other. If you calculate the entropy is 0. If you have no idea, every bar has the height 0.1, so it's a uniform distribution. And the entropy is 2.3. That's the largest entropy you can have in the system, which again illustrates that what entropy actually is. It tells us how much do we know about the system. So how much do I know that this is an 8 with a 65% probability, and I can calculate the entropy. So therefore, also, if you just think further and say, if you have no idea, then we have a uniform distribution. That implies that the maximum entropy is a uniform distribution. So a uniform distribution has the highest entropy. Just imagine you have bars that look just straight like this, which, by the way, looks pretty ordered, but it's the highest entropy you can get. So it has nothing to do with order, disorder. It really is just the amount of information or the lack of information you have from a system. And that's what you can really see in those histograms. So I really encourage you to do that, to take a look at the histograms. So that's a 7, and it's very likely that's a 7. And here's a point about a training set. In English, that's a 7. In German, that's a 1. So that's a very important difference. I don't know if you have been aboard in Europe or so, or you know some German people. This is a 1 in German. A 7 would have an additional bar here. So if you would do this with numbers written by Germans, this would be a misidentification. So that's a bias you have in the data set. And that's a very common problem. You certainly have read about biases in AI. This is a small example for that. Of course, there's examples which are more serious, but it's not trivial. It's not trivial at all to select the correct data set and also to label it correctly. And this is an example here. So this is in German, it's not a 7. And of course, then we have other values, 5 and so on. So we have a few misidentifications. You will have this. But of course, most of the time it should be correct. So a homework, if you want, try to set up a network which is a bit more complicated, and which can then tell the difference, or you train for the difference for cats and dogs. So exactly what we did here, and evaluate the results. All right, so that's our code, and I hope your code works as well. If not, again, then just download it from my GitHub repository. But now let's take a look at the TensorFlow version of LeNet, and I also want to show you that. So let me therefore just go back to our Python Spider user interface. So that's our own LeNet. That's why we call it my LeNet. And of course, I also show added LeNet from TensorFlow. So if you use TensorFlow, not sure whether I have done it already, you just call the layers, you call the losses, how you calculate the loss, what kind of network we want to have. So our network is very straightforward, so it's a sequential network. Then of course we call the data set. We have some plotting, and then I also want to call it my LeNet, but this time it's from TensorFlow, and it has the same structure. So we start with convolution layer, and we start with the number of filters, the kernel size, and the stride. And we also add the activation, which you just add directly after the layer. Then we have average pooling. Then we have the flattening. Then we have the dense layer with the 84 neurons. And of course, the output is the number of classes. And we also say that we, at the end, want to have a softmax. So that's our init. Then we set up the learning rate schedule. Then we set up the optimizer. And we want to have, again, the accuracy and the loss as an output. So that's our network. If you don't understand this part, never mind. It is kind of taking the functionality of this superclass and kind of using it here in our method. So if you don't understand, so you don't need to understand what it actually does, just ignore it. There are lots of nice tutorials about a super method. So we just use, so to say, information we have from the other classes. Okay, so then we initialize our network. Then of course we call the data set. And then I added a class that says model, which runs the model, creates a new plot, and evaluates the model. So when I run our LeNet, that takes a day or so, I would say. Then you have a very nice result. So let us now run this here, and let's see how long it takes. So we just run our LeNet now. So I would say import LeNet TensorFlow SL. And then we, first of all, want to set up our model. That's the init. So that just creates the sequential network. Then we want to run it. And let's say with 20 epochs. And you will see how fast it goes. So again, it's relatively slow on the computer because I'm recording. And we want to see the plot soon. So let me just speed this a bit up. So it first of all shows you the model so that you really see what kind of model you have, that you did the right thing. And now you can see the different epochs with the different iterations. So here it has a few more iterations. So that's the first epoch out of 20. Then you have the second epoch, the third epoch, and so on. So you see it's pretty fast. So it's actually 100 times faster than our code, because of course our code is not optimized for runtime. So let me therefore just go back to our screen where we have the PowerPoint. So I wrote a little module for you that calls the LeNet from TensorFlow. So just the very standard method how to do that. It's a sequential networks, nothing complicated, very small. And then it just calls the data. There are actually 2 lines. Be careful that you have to explicitly say that the class vector is categorical, because otherwise you get weird unrelated error messages. And I would really recommend to do that. So that's why you have these 2 lines. So this will be the error message, and that's really hard to understand why you get this error message. All right, and then we have the model part where we have the run methods and the eval method. And as I said, like with 20 epochs, that's fully sufficient and you get a really nice result. So what is the result you actually get? So let us wait for our code and let's see what we get. So let's return to our LeNet, and then let's see what we have. So we are almost done. And also here, want to speed this process up a bit. Oh, the code is done. After 20 epochs, we have an accuracy of almost 98%, and it also creates plots. So we have the accuracy from the training, and then we have validation. So in between, it also checks what the actual accuracy is, because the accuracy for the training is just for the training data, and the same plot for the loss. And if we take a look at the time, that's 100 times faster. And then we can also evaluate it by randomly taking 50 images again and comparing the predicted class to the actual class. And the important part is that it's data which has not been used in the training process. So it just does the evaluation, which again is relatively fast. It's only slower here on the computer, but I also want to show you the result later. So we have the our plots, which shows the accuracy and the loss, and again it's 100 times faster than our code. And the plot for the evaluation just picks a certain number of data points or images randomly and compares the probability for the actual class for the determined class with the actual class. So for example, let's take this value or this image here. It's a 2. That's the true class. That's the probability for the prediction. That's a 2. So it's first of all pretty accurate, but it's also the right correct identification. That's what you can see here with the colors, because it's in green. If it's not correct, it would be red. So we should see lots of green numbers, and it's always pretty close to 100%. So 99, 100, 99 again, and 93 or so. So if we just go back to to the other screen now, you will have the same result. Then you have all these probabilities. So that's the LeNet, and again, the architecture is the exact same that we built with our self-made neural network. Of course, it's not optimized for speed. This is something we could probably then also discuss in another tutorial. And I want to show you how to speed up our code. There are different ways how to do that, but the biggest part is the for loops. So we definitely should not have so many for loops and avoid them as far as possible. That's what it really makes the code slow. All right, so our LeNet works, and here are my last words about the lecture. So that was a very simple example of a network. Of course, the CNNs can have different architectures. So for example, there's the inception architecture, where we have, so to say, like really an inception between different layers. So we just bypass 1 or 2 layers. Then we also have segmentation CNNs, where we categorize not entire images, but pixel in the images. So that's called semantic segmentation. And also we saw what influences the training. So first of all, the training parameters, of course, learning rate, the decay to momentum, and also in our case, the L2. So that was the correction for large weights, so that we penalize large weights. And then another thing I want to show you is the initialization of the data, of the of the weights, or what you can also check if you like. So, for example, if we start the initialization of 0.1 times normal distribution for the weights, then you will get the result that I just showed you. If you do this with 1 or 10 times, then the training is a lot worse. It even might lead to fluctuations. And that's actually not expected in the first place. If you think about it, it's so sensitive to the initialization of the weights, but it actually is. So that actually plays a role. And of course, the architecture plays a role. So the number of layers, which kind of filter, which kind of pooling, that really depends on the problem. So not every network is suitable to solve every problem. So you actually always need a specific architecture, even if we just stick to CNNs for categorization. When you have segmentation, it's again something else. And of course, if we have language models, it's a completely different architecture. But even within CNNs for categorization, the architecture matters. And also what I showed you is like the sample, so how you treat a sample, so like the mini batch size, the number of iterations per mini batch. And also for the training, be careful about the training set. So diversity is the key. So I explained this already a bit when we looked at the images of cats and dogs. So it's not sufficient if you just have a nice image of every breed of dog or cat. It has to have images, or it have to be images in weird angles. It's blurred. All the different classes have to be there with equal frequency. That it also does not disregard, for example, particular kinds of classes which are rare in the training. And we actually do this kind of artificially, so these weird angles and blurred. It's called augmentation. So you can increase the training performance and can also work with fewer images if you take those images, just cut out random parts, stretch them, turn them, blur them, whatever. So really take one image, turn it, stretch it, blur it, cut things out randomly, do the same thing, turning, stretching, blurring, 10, 50 times with one image, and then do this with all the other images. So that kind of increases your data set. And this is called augmentation, and that plays a huge role. It makes a huge difference. Their augmentation codes, I don't know. I always wrote my own augmentation codes because then I know exactly what they do, and also for the specific problem, you also sometimes have to apply specific augmentation. So I'm maybe a bit stubborn, but I always write my own augmentation routine, which is also not really difficult to do. But do augmentation. And when you really train a neural network, that's a very important thing. And also be careful with batch effects. So what we also did not do here is that we, for example, normalized all these images before we fed in the data into the network. So for example, if the pixel values in 8-bit goes from 0 to 255, that's something else as if they go from 0 to 1, which also might reflect all the different colors you have in the image, but it's just a different scaling. So the dynamic range matters. Then maybe if they're from different sources, different cameras, kind of normalize it. So there's always a pre-processing routine. And also here, the details are very important. It's like equally important, like augmentation, of course. Labeling is also very important. Garbage in, garbage out. So if you don't label it accordingly and very accurate, then of course the network doesn't know what to learn. And that has a lot to do with experience. Of course, everyone knows what a cat or what a dog is. But it depends already how you, first of all, show a dog, if it's one particular breed, and it's always for example, next to a human, then it's been identified as this breed if there's a human. So that's not a dog who's identified. Then also labeling if it's not so obvious. So for example, I did this for microscopy. There was cryo-EM images, and people were selecting them in the old days, like per hand, taking a look. They took a look at those images, said it's good and bad, or like medium, and we can use it for calculating the structure or not. For example, if there are some ice crystals, if there's some streaks which are really easy to see, but like ice crystals or just a denser region of ribosomes, or so it's not actually so easy to tell whether it's just lots of ribosomes or ice crystals. Actually, only a person of experience can do that and can really label, is it a good image or a bad image? And I did a test with bachelor students, master students, postdocs, and senior scientists. And it turned out that the senior scientists are way more consistent in labeling than the master students and the bachelor students, because it has to do with experience. Of course, labeling is the thing that's been outsourced the most because it's tedious and you just need manpower for doing that. But really take it seriously. Experience matters. As I said, had the example of different students and scientists, and the accuracy, the difference in accuracy in this case was from 60% up to 98%. So it really matters a lot. And of course, the amount, the more data, the better. That's pretty simple, but these are the rules. So, and if you take all those 5 golden rules into account, then I think you will be very successful with your project. So that's it. I hope you understood now, or you understand now how it all works. If your code doesn't run, again, it's all on my GitHub repository. Feel free to download it, and also feel free to tell me if there's some typos in the slides, in the code I showed you. That's always possible. It's been hundreds of lines of code. Please let me know. Other than that, thanks a lot for your attention, and I hope you enjoyed it.